Good morning. Hi, thank you all for coming. Welcome to Advanced Pattern in Async Programming. So a little bit about us. My name is Assaf Ronen, and I am an independent consultant.
My name is Michael, and I'm an architect at AppsLayer. So just before we start in the talk, you should remember you should vote for the best talk today. Don't forget to enter the site. So today's agenda would be quite simple. We're going to show you a set of useful patterns we learned over the past few years dealing with asynchronous code. We'll see how to apply those ideas, those patterns in your system to enhance your resiliency. And the last one, to introduce the library that will contain all the patterns we'll show you today. Actually, this library contains more patterns, but we decided to take 5 patterns. We thought it's good to highlight them and explain them. So a bit of introduction. When we're dealing with asynchronous code, there's a few concurrency models we can use, such as the actor model or the CSP, and futures, which will be focused today on this talk. So we both used to work for Outbrain, which we decided to pass to asynchronous code using a library that we wrote called Obic. In Obic, we implemented our own futures library in Java, and with that library, we created and implemented a set of patterns that we decided to export to a standalone library working with Scala's Future. So the first pre-pattern or pattern 0 for this talk would be schedule, one of the primitives for the other patterns we'll show you today. For most of you that are familiar with Java, in Java we have Java Scheduled Executor Service to schedule tasks in the future. Scala actually does not have any API to schedule tasks. We needed ability to reference time for futures to whether to compute a value in the future or compute a future in the future. That's why using those 2 APIs that we created called schedule, where the first API actually takes a duration and a callable that produces a value. The second API is similar to called ScaleUA. ScaleUA actually taking a callable that produces a future. The differences between those APIs is that the second method is actually just doing flat map internally, so we won't have nested futures when we want to schedule a future task. Let's take a look at a basic usage example. So basically here we're scheduling a task that will sample the time in 1 second. Then we're waiting for the future to complete, and we see that basically the current time would be in 1 second differences from the sample time we checked in the future.
Okay. So the second pattern, or pattern number 1, is called wait timeout. So to start with, how many of you are familiar with futures in Scala anyway, and are writing in production? Each and every one of you. Excellent, excellent. Okay. So you're all aware of the fact that basically when we are issuing or creating a future in Scala, there is no time limit on that future. If we're going to wait for it, we'll not actually wait for it, right? We are mapping or flat mapping over it. We basically can wait forever. And if we are using future in production, that is not acceptable, right? We have to define SLA per operation, and we have to define how much time we are willing to spend on it. And if we cannot return, if we don't get a response in time in the defined SLA, it is actually better to return an error instead of waiting forever, right? So to add the capability of timeout to the Scala future, the next pattern actually adds another method with implicit class in Scala called wait timeout. And wait timeout actually allows us to define a timeout on that future. And it will return a new feature that will contain either the original result, if it has return on time, or a timeout exception. Okay, does that make sense? Excellent. And the important thing here to remember is that we are not canceling the original future. Why we're not canceling? Because Scala Future doesn't have a cancellation mechanism. Okay, so basically your future will be a new one that will contain a timeout exception, but the original one will continue to run. Right? It is not the best thing that you can expect for, but using Scala Future, that's the best we can have. So let's see a simple example. The first one is, again, scheduling a future into 1 second into the future, and we are limiting the amount of time that we are giving it with 3 seconds. Now, because it will return in 1 second, we don't have an issue here, and we will actually get the result back, right? So you can see that the result of the future is the hello that we are producing in the original one. The second example is the not so happy example, in which we are scheduling a value 300 seconds or 5 minutes into the future, but we are limiting the amount of time that we're giving that future with 1 second, okay? And obviously the original result will not come back in time, and at this point we will get a timeout exception after 1 second. Make sense? Excellent.
So the second pattern is sequence. For all of you that are familiar with Scala's Future, you know that Scala's Future actually already has a method called sequence. The method gives us the ability to aggregate independent futures into a one list contains all the results. It actually has two main drawbacks. The first one, for those of you who actually saw how sequence in Scala is implemented, it's quite easy. It just takes the sequence of future and folding it left, thus creating a chain which just serializing all the futures into one chain. It doesn't give us the ability of fail fast. Means that if we have 10 futures, 10 slow futures, and the last one failed immediately, we'll wait for the whole chain to fulfill, to be complete, to realize that the last future actually failed and return that failure. Second one is the behavior of sequence. What if, for example, we want to take only 90% of the results? It's good enough for us to decide which percentage of the values is considered to be a success and not failing the whole computation only because a single future failed. So for that, we have a new definition for sequence. So similar to Scala Future, we are taking here a sequence of futures, and the second parameter is a stop condition that I'll explain a bit later. You can see here that there's another method called collect, which gives us the ability to aggregate map of futures for cases that we want to mark our futures. Sounds okay? Great. So the first stop condition, fail on error. It's actually the similar Scala's behavior, but comparing to that, it fails immediately. Means that if we submitted 10 futures and one of them failed immediately, we'll immediately return that failure and not wait for the slow futures to be complete. Second one, stop on error. Means that once we occurred a failed future, we return in all the successful values back to the user. So in a chain of 10 users, when one future failed, we return all the other successful futures that returned, that fulfilled. The third one, continue on error. Continue on error says let's ignore all the errors. Means that whatever the chain, whatever the sequence we're given, we're just ignoring all the failed computations. Means that we'll wait for the whole futures to be completed and then return only the successful values. Let's take a look at the definition. So that's actually the trait that defines the stop condition. So as we said, fail on error fails immediately, stop on error just stops whatever we are occurring an error, and continue on error ignores all the errors. This gives us the ability to choose the strategy of handling errors in our sequence execution. Here's the first usage example. So here we actually have 3 futures that one of them is a failure. The first 2 features are slow futures that scheduled in 1 and 2 seconds. In Scala's sequence method, we would wait for those 2 seconds to be completed to realize that the third future already failed. Here we can see that once we call the sequence method with fail on error, we'll see that we'll fail immediately. So thus we're waiting only 10 milliseconds for the await to see that our returned future already contain the failed value, which in this case is service exception. The second usage example is using stop on error. Stop on error gives us the ability just stop on the first error. Here we can see that we have 3 features that the first one is scheduled in 1 second, the failed feature scheduled in 3 seconds, and the last feature scheduled to 5 seconds. Means that once we code to collect method with stop on error, we'll see that we manage to collect the first completed future with the value first. When the second future with the runtime exception will be fulfilled, we'll stop the execution and return a map of a single value that will contain the first future. So the third usage example is using continue on error. Here we can see that we have 4 futures that already been fulfilled. And once we code to collect with continue on error, we'll see that we'll manage to collect all the successful futures and ignoring the failures. Thus, we're getting back a map containing the 3 succeeded values. But what if you want to collect actually all the results, whatever if they failed or not? For that, we're giving another API called sequence_all and collect_all. Sequence_all, comparing to sequence, returning a future of sequence of try, means that we're just returning the try of each computation. We're waiting for the whole future chain to be completed and returning you the try, marking their state, whether it's failure or not. Collect_all is similar in this manner, just collect_all takes a map. So let's take a look at usage example. Here we're just taking the sequence of those 3 features, and we can see that we actually, the final result is getting all the futures back, and here we're just making a simple partitioning, splitting those groups into two sequences, one with succeed features and second one with failures. And we see that the good results would be a size of 2, and the bad results would be a size of 1, since we only have 1 failed future, and the rest of them succeeded.
Okay, so the next pattern is parallel sequence. So if you think about it, if you'll use the previous pattern, we would see that all the future that we try to collect together basically run together concurrently. But sometimes we don't really want that, right? That level of concurrency is too high, and we want some kind of mechanism to control the level of concurrency, right? So for example, if we want to issue 1 million concurrent requests to a system, we would probably overwhelm it, and it will either crash or throttle us, which is not something that we want, right? So what we need is some kind of mechanism that will allow us to define the level of concurrency and then run all the future until they all complete. So let's look at the API. Again, 2 versions. One is using a sequence, one is using a map. What we're getting here basically is a sequence of elements that will be used as an input to the production of the future, because we can't really get the list or the sequence of the future, because once you get it, it's already running, right? So we need some kind of mechanism that will lazily create it. So that's how we use it. So we are getting a list of input to our producer. We have a producer that uses each of those elements to produce the future. We have the level of parallelism, right, which will be the maximum level of parallelism, and again, the stop condition that we've seen before. And what we are getting back is same as the previous API, a future of a sequence or a future of a map. Make sense? Okay. So let's see a simple example. What we are trying to do here is basically send 10,000 queries to Google. And we know that if we'll send them all concurrently, Google will throttle us. So what we are doing here is choosing the level of concurrency to be 10, issuing those requests with continue on error or stop condition, which means that even if some of the requests will be blocked or will be throttled, again, we will collect those that will succeed. And again, what we're asserting here is that at least 50% of the result will come back, hopefully much more than that. Okay? But what will happen behind the scene that in every given moment, only 10 requests will be in progress, will be issued to Google.
Retry. So all of us know that I operations may fail, and we can easily enhance our system by just retrying those operations. Some of the errors we occur are volatile and not persistent. So we can just try to retry our operation again and again until we succeed. That's actually how we transform at most one semantics to at least one semantics by each time getting a failed future, retrying it until we're succeeding. So the retry definition here is quite similar to most of retries you probably saw, but the main advantage of our method is the retry policy. Here we can see that we're taking the retries amount, the producer that upon given an iteration will return us a future, and a retry policy. Retry policy is our ability to define how we want to retry. We will show you a bit later. The second method is retry with partial function that accepts exception and gives us back a retry policy. Means that not for all exceptions we want to retry. Some of them actually are persistent and may cause a system to be just to be in bad condition. So we have the ability to define for which exceptions we want to handle and for which not. Let's take a look about the policy definition. So here we have 3 strategies. The first one is immediate. Means that whatever the future failed, we just retry it again. The second one is fixed. Fixed gives us the ability to set up sort of a slip between the operation to give us some time to relax, to give the system a time to be recovered till the next operation will happen. And the third one is exponential. Similar to fixed one, it just increments the duration time by a factor of 2. Let's take a look at the first usage example. Here our policy says we'll have a fixed delay of 1 second. When we're trying to execute our retry method, we see that for the first iteration, we're failing with runtime exception. We'll wait 1 second before we're retrying. The second execution will fail again on retry exception. Means that we're already waiting for 2 seconds. The third iteration will succeed with great success. We can see here that at all, we're going to wait for 2 seconds. And the final result would be a great success. The second usage example is using the retry policy that gave us the ability to define a function. Here we see that we're handling only timeout exception and no other exceptions at all. On the retry call, we see that for the first iteration, we're failing actually on timeout exception. Decline, the result didn't come back in right time. We're trying to retry it again in 1 second. The second iteration fails with IO exception. It's something that we haven't expected to happen, and we'll just stop the execution. We'll see that eventually the result of the future will be the IO exception itself. That's clear? Great.
Okay, next one is double dispatch. So whenever we're executing an RPC call, not all calls return on time, right? We've talked about it before, that we have to define an SLA on every call. So what happens when we do define an SLA? If we would measure the amount of time that it takes us to call this remote endpoint, we would see a distribution of latencies that some of them will come back on time and some of them won't, right? So if we would look on try to analyze the reasons why those answers that didn't come back on time didn't come back, we would see that most of them fail for reasons that are either volatile or local. Now, what does it mean? Volatile means that the reason will disappear shortly in time, meaning that if we will retry the request again, we would get a successful result in time. Local means that if we are issuing a call behind a load balancer, maybe one server is unresponsive, but if we will call again, the load balancer will send the request to another server and it will be responsive, right? So there is a great incentive to basically issue more than one request, and there is a good chance that if we will issue more than one request, if the first one is not successful, the second one will be, right? So basically what we are doing here is trading the load of the system with the responsiveness of the system by basically creating more than one call. So the algorithm itself is pretty easy. Basically, we are sending the first result, which is getting routed to the first node or first server. And after a predefined period of time, either we got a successful result from the first server, or we are issuing another one that would probably go to a different one. And then what we do is basically wait for the first one of them to return. Okay, make sense? So let's look at the API. Basically, we are taking a duration, which is the amount of time that we're waiting for the first return, first answer to get back. A producer, which is basically a lazy future, right? Because we have to recreate our call. And again, this mechanism only works with idempotent calls, because basically, if that call is not idempotent, we might call it twice, and it will corrupt state. Let's see a very simple example. What we see here is a call to double dispatch after 1 second. And the future itself produces a slow response the first time we call it, after 3 seconds. But the second call returns faster after 1 second. So because we're using double dispatch, it will wait 1 second for the first call to return, which will not return because it is returning after 3 seconds, and then issue the second response, which will come back after 1 second, which means that we will get a response after 2 seconds, which is faster than 3 seconds, right? Make sense? Still with me? Great. So what we've done here is improve the latency, right? We've shortened the latency from 3 seconds to 2 seconds, which is nice. Okay? Okay, so let's take a more elaborate example, and this one is complicated, so hang in. What we see here is a graph that depicts the distribution of latency when we call a remote system, right? So basically what we see on the x-axis here are the percentiles, and on the y-axis is the latency, measured in milliseconds in this case, okay? Make sense? Excellent. So what we see here is that the greater the percentile is, the longer the latency is, which makes sense, right? We always have long tail of long calls that takes basically forever. And so for this specific system, we see here that the graph here is not really clear, but I'll try to explain. The 90th percentile stands on 50 milliseconds, which means that 90% of the calls, of the remote calls, come back under 50 milliseconds, okay? And the 99th percentile come back after 100 milliseconds, okay? So again, out of every 100 requests, 99 will return below 100 milliseconds, okay? That's the meaning of this graph. What it's also said that we have defined our SLA to be 100 milliseconds, which means that if we're gonna call this system as is without changing anything, for every 100 requests, 99 of them are going to be successful because they're going to return in under 100 milliseconds, and 1% is going to be failure because it's going to return after 100 milliseconds. Okay? Make sense so far? Okay. So what we're trying to do here is to improve the resiliency, actually improve the responsiveness of the system. So how do we do that? Let's take an example. So what we're doing here is using double dispatch and defining the initial latency before the second call to be 50 milliseconds, okay? So we know, looking at that graph, that after 50 milliseconds, 90% of the calls will come back in time. And for 10% of them, we will issue a second response, okay? Now, what will happen with this second call? We know that this second call basically behaves the same way as the first one does, right? Because it adheres to the same graph, which means that if it has to uphold a latency of 50 milliseconds, right? Because we only have 50 milliseconds after we've waited for 50 milliseconds, 90% of those calls will come back on time, right? Because again, we know that the 90th percentile of the call returns under 50 milliseconds, which means that out of the 1% that have failed for the first call, we have created another 90% out of the 1% that is successful. It is complicated, I'm sorry. But if we will combine those two numbers together, we will see that we are getting 99 responsiveness from the first call and another 0.9 percentile from the second one, and together we get 99.9% successful calls, which means that we have improved the responsiveness of the system by a factor of 10. And we've only increased the load of the system in 10%. Why? Because for 90% of the call, we will not issue a second call. Okay? Make sense? That was the most complicated thing that we have here. Okay, so if that makes sense.
Great. So it's important to mention that all those patterns being used in production. So most of you probably thought, what's double dispatch? It's actually helped Outbrain a lot. And all those patterns you saw and the other patterns that exist in the library actually being used every day by the developers. Our future plans for the library is actually to add circuit breaker, which is also a basic primitive to distributed systems. Also resource pool. If one of you try to write a synchronous resource pool, it's quite easy, but try to make it a synchronous one, it's getting a bit tough. And we also accept pull requests, so feel free to go to the code, check out, and give us a comments. Thank you.
I think this double dispatch pattern also has some extensions that might be interesting when you have, for example, a calculation that's difficult to do, and you kind of are happy with an intermediate result that's maybe not optimal but close, and you can run it on several systems and then select the best result. Or you can run different algorithms on different systems and then select the one that comes back first. So I think it's a very interesting and useful idea.
Thank you.
Thank you, guys. Can you please maybe elaborate a little bit on the implementation details of your sequence thing when you failed fast? Mm-hmm. How's it implemented?
So basically the trick here is not using fold, right? What we do is concurrently wait for all future to return, and basically the first one that comes back actually triggers the result, right? We're using basically an atomic variable behind the scene to trigger the first result.
Okay. And another question. So you mentioned that it's not possible to cancel Scala Future. And then you have another combinator which kind of uses producer, which mimics like lazy future initialization, right? So is that possible to cancel in that case? I mean,
well, no, because you've already issued it.
No, but I mean like the producer didn't issue it, right?
Well, if we are using with timeout, basically what it means is that the original future is already running, right? Even if originally we are using lazy future.
Maybe if you can go back in slides to show that. I don't remember exactly the name of that combinator.
So for retry or double dispatch, for example.
For the producer, the one where you had producer from something to future. No, it's not a sequence. I think it's the next one. Yes, this one. So here, like your producer doesn't immediately start a future. So I'm just asking.
Right. So
if cancellation supported here,
it's not really a cancellation in terms of if the stop condition is fail on error and we still haven't produced the other futures, they won't just happen. But once we started to execute in the future, once we call the producer, it will start running. It's not possible for us to interrupt or cancel it.
But like if you combine that with like timeout, then you have this thing and then
so
timeout.
So the timeout is external. You can compose those patterns, but timeout does not aware of the internals of the previous method. For timeout, it's like I'm getting a future, I'm applying timeout to it. Okay. It doesn't know how to notify the previous chain to say, hey, I'm going to timeout you, please stop your execution. But for that, we just introduce stop condition also to this method. So you'll be able to decide the strategy of the execution. In this method, if you just go with fail on error and one of the batches will fail, we'll just stop the execution and won't spawn the other task.
Okay, got it. And how would you compare that to something like Monix? Like where would you say like you should No,
Well,
use that instead of, or like.
Yeah, basically Monix is an excellent implementation of Future, and if you are using it and it does have time limitation mechanism, so go ahead and use it. But if you are using Scala Future because you know it or because you have to, and you don't have any other mechanism, then by all means use our library. Right?
It's also worth to mention Twitter also have their own Future implementation, and thus contains part of the patterns we showed you here today. But again, if you're using Scala Future natively, and most of the third-party libraries actually using Scala's Future, it's quite easy just to take those patterns out of the box and using them without modifying much your code.
Hi there, great presentation. Can you tell me please, have you used Cat's IO monad?
No.
Okay, thank you.
Thanks for the talk. I have a I have a question. I have a question. Is your scheduled futures based on Akka scheduler?
Great question. We actually have a few implementations. So the base rate I think shown in one of the examples is scheduler. And we have currently two implementations, one using Java's scheduled executor service and the second one using Akka's. If you're using Akka in your system, you can just use that implementation. We don't enforce that. It's actually an optional dependency in the library.
Thanks.
Yeah, hello, really good. The double dispatch, it looked like the benefit that you get is quite dependent on the shape of that curve, right? So that depends on you knowing what the responsiveness of your downstream service looks like. And obviously that could change day on day, week on week. So is there something that maybe would help you to determine at any point in time what is the correct value to use there, so that either you're not loading it unnecessarily, but you're still getting value?
So yeah, absolutely, absolutely. So first of all, yes, there are type of systems or occasions in which the error doesn't look like that, right? If you have like a total failure in the system, double dispatch will not help you. Actually, it will do the other, right? And another thing that you've mentioned, and you're absolutely right, one way to extend that system or that service is basically to measure the graph all the time, choose the right percentile, and out of it, extract the amount of time that you want to wait. Absolutely, yeah.
Can you please suggest some test tool to test scheduled code without thread sleep, for example?
And that's a good question for both of us. We're just using await. We don't actually trying to compose async chains and hoping for some system to do it nicely. Just doing .get and waiting for the result.
But it increases times of tests, yeah?
Yeah, yeah.
Mm-hmm. Okay.
Not efficient tests, but at least they're clear.
Thanks.
I can just answer that question quickly. I mean, maybe like just give a hint. So we talked about Monix, and it has this abstraction of a scheduler as well. So they have test scheduler, which you can pretty much say like, oh, I want to that much time passed, like you just call tick or something like that, and then it just simulates. But because the Monix task is lazy, you don't actually use time, so it's super fast, but that works. And I mean, like, it doesn't mean that you have to use Monix. You can just do sort of same thing.
Cool. Maybe the last thing about double dispatch, and we'll finish here. So as Asi mentioned, we should and we could measure the latencies in runtime. One of the ways is just statically analyze your graph and see that 50 milliseconds is your percentile, is your native percentile. Or you can use implementations such as Gilsten HDR histogram to measure over time your latencies and produce the right percentile for double dispatch. Second one also is the strategy, how you do. We do assume that the load balancer will spawn the request to different nodes. But what happens if we have a small system, a small cluster of 3 nodes? There's a chance that one of the requests, like the double dispatch, will send the same request to the same node, since the load balancer decided to spawn those of 2 requests to the same node. We can also avoid that by keeping the nodes in ourselves, like in the code, in the memory. Sorry. If you're using a service discovery tools like console, you have the ability to implement the client-side load balancing. And if you do so, you always know to which node you send the request, and you can avoid sending the same request to the same node by just implementing this strategy. There's a lot of extension that we actually implemented back then, and it was quite hard for us to export all of these ideas to this small library. But know that those patterns are small enough and composable enough for you to think how you can take them and improve them and just improve your system resiliency. That's all. Thank you.